So first, let me just say a little bit about myself. I, like Dave Brain, came in on this project not grabbing my ticket from the ticket person, the travel agent at Space Sciences Laboratory and rushing off to a launch, but rather before anything ever happened. When we got into a room, and I think Bruce set the tone very early on by saying, you know, we want to design a mission, we want to do it the right way, we want to start with a blank piece of paper and try to design this properly. And there's just a tremendous amount of thought that goes into something like this. And it's hard to really appreciate that until you actually do it. And so I've really gained an appreciation of what it really takes to do something like this. And so the Particles and Fields suite actually comprises the lion's share of the entire payload on the spacecraft. As Bruce pointed out, we're distributed all over the spacecraft from the ends of these 7-meter booms for the lander probes. SWI is on the end of a 1.5-meter boom back here, solar wind electron analyzer. SWIA is here. EUV you can't really see in this image. I'm not even sure if it's represented in the model. It's just a small box. I'll show you a picture of it in a moment. The Solar Energetic Particle Instrument has 2 identical boxes, one here and one here. Static is on that APP here. It shares the APP with the IUVS and NGIMS, which you'll hear more about tomorrow. Magnetometers are at the end of these little mini boomlets to stay as far away from the spacecraft as possible. Again, as Bruce already mentioned. I'm going to show you this cartoon one more time. Maybe the third time's the charm. I thought, you know, the speakers that came before me did a good job of explaining sort of how this all fits together. Blue is the neutral escape, red is the ion escape. But I just wanted to sort of array the instruments around the chart to give you an idea of that there's actually a physical box, a physical instrument that was constructed and designed to make these measurements. So we go up here, we start with EUV. This measures the extreme ultraviolet light from the sun. That's this little squiggly line here. The solar wind ion analyzer measures the solar wind. It measures the density and temperature of the solar wind and the flow velocity. SWIA, the solar wind electron analyzer, measures the solar wind electrons. It also has another role that it shares with the magnetometer, which I'll describe in a little bit more detail later in my talk. But they work together. You know, you have these magnetic fields, and of course magnetic fields are invisible. You can't see them. Yet, all the charged particles respond to them. And I'll have a dance later. I promised I would do a dance. So you're all going to have to wait for the dance. But the charged particles, even though you can't see the magnetic field lines, they respond to the magnetic field lines. And so it's important to set the stage to understand, to make something visible that's invisible. And so the magnetometer and the electron analyzer make the invisible magnetic fields visible so that we can understand how they control the processes, loss processes. The magnetometer, of course, measures the magnetic field and tells you the strength and direction of that field. But the electron analyzer tells you how the field is connected. So whether it's one of these closed loops where both ends are anchored into the crust, the electron analyzer can tell you that because it can look at the population of electrons on that loop. And if the population of electrons on that loop are ionospheric electrons, you know you're on a closed loop. If one of the loops opens up, like out here, then you see solar wind electrons coming in on that loop, and the electron analyzer can see that. And so with these two instruments together, we map not only what the magnetic field is at the spacecraft, but how it is on a larger scale. So it's a very important thing for this understanding the ion escape. And then over here, Langer probe and waves. So as Bruce mentioned in his talk, it's very important for understanding the temperature and density of the ionospheric electron population, the thermal population, for calculating the chemistry that gives rise to hot neutrals that escape via this photochemical escape. So it's a very important measurement to make. And it also measures waves. And waves can be important for heating ions, heating the plasma. And so the waves can be driven from the solar wind. The solar wind, you think, you know, you're going to see all these charts where the solar wind is this steady stream coming from the sun, but that's not it at all. Here's part of my dance. This is the one I wasn't planning. So the solar wind is actually buffeting. It's always buffeting. Okay, so it's never the steady state. So the magnetic field is rotating and the solar wind is doing this. And so that drives waves. And as the solar wind encounters the planet and passes through the shock, all of this buffeting creates waves that propagate down through the system. And the waves can go all the way down into the ionosphere.
What's the time scale for the variations, the buffeting?
They can
days?
They can happen on many different time scales. So from just a few seconds to much longer time scales. So yeah, over a broad range of time scales. Let's see. So so the Lamier probe in waves measures the propagation of these waves down into the ionosphere, and looks for evidence of ion heating. We want to understand how the ions, the ions are formed in the ionosphere. They don't have escape velocity yet, so we have to understand how they gain the energy to get escape velocity to leave the planet, because you can't leave the planet unless you have escape velocity. So the heating and energization of the ions is very important. And then, of course, static, the superthermal and thermal ion composition analyzer. Does an important job in measuring the ions, and not just measuring the ions, but measuring their properties, what their mass is, what direction they're going, what their energy is. And it takes all of this information to piece together what's going on with the ion escape. Okay. Was it clear at the third time, or no? Okay, first I want to talk about pickup ions, and I have a completely different take on this. And hopefully maybe the third time's its charm here as well. And so, so the way this works is you have the solar wind coming in at 400 kilometers per second, but remember it's buffeting as it goes in. The solar wind has embedded in it a magnetic field, and I've done put a vector diagram up here. So the magnetic field vector is coming out of the page. So it's what I call a plus BY. And this would be an away sector. So this is the sun here, and the solar wind magnetic field, which originates from the sun, goes out in this sector pattern. And you have an away field, which where the magnetic field points away from the sun, and I call that a plus BY. And then you have a towards sector where it points towards the sun. And so as the sun rotates, then a planet sitting out there will experience both away sectors and toward sectors. And so the polarity matters. And so if you have a solar wind velocity going in this direction and a magnetic field out of the board, then the electric field that generates is perpendicular to both of those. And so it points up. And so, but if you flip the polarity, everything goes upside down. And so that's why it's important to make this measurement of the magnetic field so that you understand where to look for the plume. Now, I've only shown two orientations. You can have any orientation. So that magnetic field, most of the time it's in the plane of the solar system. It's either plus B or minus B, but there can be a Z component as well, and it can rotate all around. And so when you look at Dave Brain's chart, when he tried to map an MSE coordinates, what he was doing was he was taking this electric field and trying to orient that so that it was pointing up all the time. And so that's what that's an important thing to do to understand the ion escape. And it's also important because another thing to mention here is that these pickup ions here are going to respond to the electric field, and they're also going to see the magnetic field. And so what they do is they become accelerated, they begin to gyrate around the magnetic field, and they form the cycloidal motion as they go back. And then the energies that they can achieve at the top of the cycloidal motion are quite large. For a proton, the solar wind energy just coming in, if you look at the charts, are around 1 keV, but a pickup ion can be substantially higher than that. So you can get many keV for the hydrogen and up to 50 keV for oxygen. And for the higher mass particles, you get even higher energy. And so you really get very high energies for these pickup ions.
Dave, may I interrupt for just a second?
Sure.
So the source of these ions is they are in the ionosphere and get swept up by the solar wind, or they are neutrals that migrate out, get photodissociated, and then get swept up by the solar wind.
Both. And so you have this extended corona, which extends, as Dave Brain pointed out beyond the bow shock even. And so those particles will get ionized by solar EUV, and they'll get picked up and start gyrating. And there's a process called mass loading, where the solar wind has to actually provide the momentum to accelerate those particles, and it causes the solar wind to slow down. This is the primary interaction for a comet, for example. But also, the solar ultraviolet is also doing ionization here. And this is actually an important place to do ionization because the density here is so much larger than the ion density out here, atmospheric ion density out here. So when you ionize close to the planet, you have a very large density, and so that's what gives you the mohawk. That's what gives you the pickup plume, is that you have a high density here, and I'll talk about that in a little bit in more detail later. It's also important to realize that photoionization is only one ionization process. There's also charge exchange and electron impact ionization. So all three processes play different roles in different parts of the system, but they're all important.
But in all those cases, you have a neutral that has found its way out into the corona and gets ionized in some way.
That's right. So it doesn't, yeah. So this process will work anywhere in the system as long as the particle is free to fly. So if you have an ion, say, down in the collisional part of the atmosphere, it can see the electric field and start trying to respond to the electric field. Before it can get very far, it runs into other things, so it just never gets very far. So it's hard to get that out of the system and escaping. So you need to be above the region where collisions are important in order to actually get accelerated without running into something and get out of the system. Okay, so as I pointed out a little bit earlier, just in response to your question, was that the important thing here for the polar plume is that it's really extracting ions, accelerating ions from a region where the density is relatively high. And so, so you're looking down in the ionosphere just above the altitude at which the ionosphere becomes collisional. Whoops. There it goes. Okay, so Static made a really nice series of measurements. And as I mentioned earlier, Static can measure not just the energy and mass of the ions, but also the direction in which they're going. And so what I'm going to be showing here is mass on the vertical axis and energy on the horizontal axis. And you can see there's, in this, at 250 kilometers altitude, which is above the collisional part of the atmosphere. So we're now in a region of the atmosphere where collisions are not important, where the ions and electrons and neutrals, for that matter, can fly freely. And so you get an ionosphere composition of O2 plus, O plus, a little bit of helium, although you can hardly see it in this plot. That's more of a solar wind thing, and H plus. And as you move a little bit higher to 300 kilometers, you see the composition change. You start to see hydrogen from the magnetosheath, and a less importance of the O2 plus and a greater importance of the O plus. And then this is the interesting one. As you go even higher, you start to see the ionosphere heating, which is beginning to drive the escape. And then finally, at 500 kilometers altitude, things have accelerated now and energized now to a couple of hundred of electron volts. Now, if you remember, a couple charts back. Oops, this is fine. Either one is fine. So for O plus, at solar wind velocities of 400 kilometers per second, they can get up to 50 keV. And so Static's energy range goes up to 30 keV. And so even Static at the top of its energy range can't see all the way here. But it's important to measure this initial stage of the acceleration so we understand where it happens in order to piece together the story for the plume itself. So this is a model by Shannon Curry and Yan Shui Dong which is a combination of a MHD model and a test particle model. And so what this shows is it's a steady state MHD model of the solar wind interaction with the planet, which solves for all the electric and magnetic fields in a steady state way. And then Shannon puts in test particles, test particle oxygen ions, and lets them respond to the electric and magnetic fields of the system and sees what happens to them. And so here, the prediction is that you have this pickup plume, which is, you can see at the very top here. So it originates down here at lower altitudes and then gets accelerated up to the top to very, very high energies. And then this central part here is the cold ion escape down the tail. And so it's the combination of these two which gives you the total ion escape. So an interesting part of this is that the suggestions from these models, at least, is that the polar plume could be an important part of the ion escape channel. And so, but the actual numbers to that is going to take some time to use the data to constrain the models in such a way that you can actually put a number to it.
Is zero longitude the subsolar point or the anti-solar point?
It's the subsolar point. So this is in MSE coordinates.
So when you say polar, that's because what you've observed so far is polar, but it
Right.
can happen away from the polar.
That's right. When I say the word polar, in this context, I mean electric pole. So it's the MSE pole.
Okay.
And that tends to be either the North Pole or the South Pole geographically of the planet. Tends to be. But it can be, but it doesn't have to be. It can be in other orientations as well.
Is that, so thinking about this, the surface of Mars and the fact that most of the carbon dioxide, ices and things like that are at the poles, would that affect the flux at all? Like what's on the surface?
Well, the polar plume, the source of the polar plume itself is the ionosphere just above the collisional part of the atmosphere, which is roughly at around 200 kilometers altitude. So everything below 200 kilometers tends to be collisional, and everything above that is free flying. So the source region for this polar plume is at 200 kilometers altitude. And so tracing the history of volatiles from the surface to 200 kilometers altitude is sort of beyond what I do. People do try to do that, try to go all the way from the surface to the composition in the lower atmosphere, and then how the things propagate up to 200 kilometers, which is where I start. But, I mean, in terms of this kind of modeling, you start with the 200 kilometers altitude. Did that answer your question?
Yeah, I was just wondering if there was any, like if you could see any connection or anything.
Yeah. Okay. Another topic I'm going to touch a little bit on is the observations of solar wind penetration. This is the double charge exchange. And so these are measurements from the solar wind ion analyzer. And this is at an altitude of fairly high up. This is upstream of the bow shock. And this is the measurement of the upstream solar wind. And I think maybe you asked the question how you can tell the difference from one hydrogen to another. One way in which you can tell the difference between one hydrogen and another is you see that there's hydrogen here and hydrogen there. H plus here, H plus there. One way you can tell is by their energy, how they're distributed in energy. So this is 1 kilovolt, kilo electron volt, a little bit less actually. And this is the solar wind beam, which is a fairly narrow beam in energy. And then the solar wind, of course, isn't pure hydrogen. It has some helium, so you see the helium as well. But what's this? What that is it's pickup hydrogen. It comes in at twice the solar wind speed, or 4 times the energy, solar wind energy. So this is pickup hydrogen, planetary pickup hydrogen. So one way to distinguish, even though they don't have name tags like we do, one way to distinguish them is by looking at the energy distribution. So as you go down in altitude, now we've gone quite far down in altitude now. This is upstream of the solar wind, and this is down in the ionosphere. And so we have this ionospheric population here, and SWIA does not resolve different masses. And so all the masses all come together and it measures all the ions, regardless of their mass. It only distinguishes energy. So this is the entire ionospheric signature. And you can see that in this part of the atmosphere, we're at high altitude. This is above 200 kilometers. And so it's above the part of the atmosphere that is collisional. And so, and here, this is basically the noise level. And so you really don't see anything beyond that. But then as you go even lower, now notice that we are now into the collisional part of the atmosphere. And suddenly you start seeing a hydrogen peak again. And so this is the double charge exchange. So the way it works here is in this cartoon, is you have the solar wind hydrogen coming in. This is the far upstream measurement that I showed you. It does a charge exchange with an exospheric species, and then it becomes neutral. And the second it becomes neutral, it suddenly does not see the electric and magnetic fields. It just flies right through. It's completely collisionless. And so without losing any energy or its direction, it just goes straight through. And then since it's the density goes up very much here, and you get into a collisional region of the atmosphere, the probability of doing another charge exchange and turning back into an ion to be measured increases dramatically as you get to this region. And so you get the solar wind hydrogen, then you get nothing, and then you get the double charge exchange. And so it goes in that sequence. And so this is thought to be, of course, it's a source of energy into the ionosphere, but it may also be a source of hydrogen in the ionosphere. Now, we don't know whether over time this process can add very much hydrogen to the upper atmosphere, but it's something that we're trying to calculate. Another interesting aspect that I'll touch on is the SEPs and the IMF zenith angle, and this is entering the topic of SEP shadowing and SEP interaction with the upper atmosphere. And so the motion of a charged particle in the magnetic field goes as a corkscrew. And so if the magnetic field is down the center of this room, a charged particle will, this is my dance, a charged particle will spiral around the magnetic field, and it's described by something we call the pitch angle. Now, a pitch angle goes from 0 degrees to 180 degrees. So if the magnetic field is directed this way, a pitch angle of 0 degrees is no spiraling at all. It just goes straight down the magnetic field. A pitch angle of 90 degrees is it just stays in one place and goes around. And a pitch angle of 180 degrees heads that way. And so you can have anything in between. So you have this gyration around the magnetic field line. And so the radius of that gyration depends on the strength of the magnetic field. The stronger the field is, the smaller, the more tightly gyrating it is. And it depends on the mass of the particle. The bigger the mass of the particle, the larger the radius. And it depends on the energy of the particle. The bigger the energy, larger the radius.
So gyro radius and pitch angle are not the same.
There are two ways to describe the nature of the corkscrew. So pitch angle is how much of it is directed along the field line, and the gyro radius is the size of the corkscrew.
Right.
Okay, so you can have a pitch angle of 45 degrees this way with a small gyro radius, and a pitch angle of 45 degrees this way.
But gyro radius corresponds to the energy of that particle, and the pitch angle has to do with
It's
physical velocity?
It's pitch. It's pitch with respect to the magnetic field. So
Okay.
pitch angle is just the angle that the velocity vector makes with the magnetic field.
Okay, but it is dependent on velocity.
Yeah, that's right. Okay, and it's important, or it's interesting actually to consider the scale of these things. If you have these solar energetic particles, they can come in very large energies, from just tens of keV to many MeV. And the gyro radius gets to be quite large. And so you can see for a 10 keV proton, for example, your gyro radius is relatively small, just a tenth of the size of the planet. But then as you move up in energy, you get to the point where the gyro radius is as big as the planet is. And then as you go to even higher energies, it's much larger. And so the energy, the ability of the planet to shield or to absorb the SEPs, in terms of where they land, the geometry of where they land on the planet depends very much on this parameter, the gyro radius. Okay, and so SEPs are important, of course, because they can deposit energy into the ionosphere.
Dave, I'm sure you've said, but just to say again what SEP is. I'm just doing an acronym check.
Oh, SEP, solar energetic particle. I think these have been touched on by both of the previous speakers, but solar energetic particle. Okay, so so actually this is by Rebecca Jolis, who is sitting here. She did this calculation for us together with Rob Lillis. And this just shows you the SEP protons as a function of energy. This is 1 MeV here. This is 10 MeV at the right, where they deposit their energy. And you can see that they, these SEPs come in and heat up the atmosphere at the altitudes that MAVEN gets down to, 150 kilometers, and then even below. And so they can actually, during these large solar storms, could be a significant source of energy to the ionosphere. So the interesting thing is then these are, the greens come out almost neon in this. I don't know why that is.
Very cool.
It's interesting. But these are data plots showing SEP measurements as a function of altitude and energy. And so, I should go back. So there's this magnetic zenith angle. It depends upon where MAVEN is with respect to the magnetic field line. So if MAVEN is over here, it's at magnetic noon. And this is at the dawn and dusk magnetic zenith angle. And then an angle of 180 degrees would be magnetic midnight. And so if you look at on the magnetic base side, where that angle is small, and you're on the same side of the planet as the SEPs are coming, then you get SEPs coming in at all energies without very much attenuation. Now this part in here is a kind of a more fine-tuned explanation as to why this happens, but it has to do with the geometry of the size of the gyro rays with respect to the planet. But as you go to magnetic morning and evening, then the planet absorbs SEPs in this range, and you just don't see them when you're in the morning and evening at higher altitudes. And then as you go to the magnetic night side, the shadowing happens over a larger energy range and over a higher altitude range. So this is the absorption, the planetary absorption of the SEPs. Now notice that when you get to very high energies, you don't see any shadowing at all. That's because the gyro radii are so large, but the planet has no ability to shield from these very large gyro radius particles. Okay. So the next topic I'll touch on is the aurora. And now this is an image that has already been publicly released. This is the IUVS observations of the auroral emissions. This has been given different names, but I'll use the term diffuse aurora, meaning that the aurora took place not in magnetic cusps where you might normally think them to occur, but rather distributed widely over geographic space. And so the nice thing about MAVEN is that we can make simultaneous measurements of both the auroral emissions as we fly past that region and the geometry is right for IUVS to make the auroral observation. And we can also measure in situ the particles that are causing the emissions. And so this is a cause and effect story here. This is a solar energetic particle instrument. And then you can see that there's a solar energetic electron event. These are relatively rare to have electron events like this. But you can see that it correlates very well with the auroral observations by IUVS. And it turns out, and I think Bruce pointed this out in his talk, that at these energies, 20 kiloelectron volts up to 100 kiloelectron volts, they deposit their energy down at the altitudes where IUVS infers that the aurora took place. And so at altitudes of around 100 kilometers, maybe somewhat less, these electrons will penetrate down to those altitudes and deposit their energy. And so this is almost certainly the cause of this. And then, as I mentioned earlier, the solar wind electron instrument, even though it doesn't measure these high energies, its energy range stops at about 5 kiloelectron volts. And 5 keV particles don't penetrate down to the altitudes where the diffuse aurora took place. But what they do is they help establish the magnetic topology. So this is a map from Mars Global Surveyor showing the distribution of crustal magnetic anomalies over a map of the planet. So just to orient you, this is Olympus Mons here, Valles Marineris, Elysium Mons, Hellas Planitia. So the distribution of magnetic fields, this is the radial component of the magnetic field, so you can see where those fields are. And the IUVS observations are up in this part. But what the electron instrument can do is it can give you an idea of what the topology is. So if I switch over to a map of the topology, this is also from MGS. This is based upon millions and millions of individual electron spectra, indicating, using the population of electrons on that field line to determine whether it's a closed loop forming a magnetic field. So that these are the white areas. The white areas are closed loops. And the black areas are open out into the solar wind. So these are regions where the electrons can precipitate down and cause aurora if the conditions are right. And so you notice the whole top, almost the entire top of this image is black. So these are typically open field lines. So if we go back and forth, you can see that open field lines are to be expected up in the top. So then if you go to measurements by MAVEN now, this is the solar wind electron instrument on MAVEN, it measures this pitch angle distribution. And so, as I explained earlier, 0 to 90 degrees pitch angle are gyrating along the magnetic field line. And in this orientation of the field line, they're precipitating down to the planet. So I can actually separate the electrons that are traveling down, precipitating down, from those traveling up. And so if you look at this part of the spectrum here, you'll see that the colors are much more cold and blue in the upper part of the population. So what's happening is you get this precipitating population that goes down towards the atmosphere, and then some of that gets reflected up magnetically, some of it gets reflected by magnetic fields, and some gets reflected by just backscatter. And you'll notice that at the low pitch angles, those things tend to get reflected at higher altitudes. And the ones that are more field aligned have more of their energy directed down, so they tend to penetrate to lower altitudes. And so this is absorption at low altitudes by the atmosphere. And so you can see this is the signature that you would see in the electrons for precipitating electrons and absorption in the atmosphere. So this is this observation was made right along here, this stretch of time here. And so you can see that there is some overlap with the IUVS measurements, but because IUVS is doing a limb scan, it's looking along the limb to make its measurements of the aurora. And SWIA is making its measurements in situ. They don't exactly line up perfectly, but you can see that the magnetic topology, both from what we expect based upon MGS observations and actual measurements of the topology during the time that the auroral observations were made, indicate that we have both the smoking gun, these are the electrons that are doing it, the conditions for the absorption are there, and the auroral emissions are observed. So we get all the way from cause to path to effect using MAVEN measurements, which I think is a really powerful way to constrain problems like this.
Gain by having a longer time base for amassing these observations? Do you get a more complete picture over time?
Yeah, and in fact, getting a long time base of observations is really important because the conditions change all the time. And so, as in Dave Brain's talk, he was talking about how the mapping into MSE coordinates is important to fill in the phase space, we call it, or the range of conditions that go towards trying to understand the process in detail. And so the same thing is true for here. So we want to try to measure the response of the system to a whole variety of different inputs. And so that takes time to build up all of that information.
And in terms of characterizing the polar plume, will you benefit from having the periapsis of the orbit precessed in such a way that you're physically over the electric field poles?
That's right. And so the observations that I showed early from the static measurements were at the very root of the plume, right as it was forming. And so, of course, static can measure ions all the way out to 30 kilovolts. And so as the orbit precesses and brings the higher altitudes over the plume, static can make measurements of the higher energy accelerated particles over the plume.
That are farther away.
That are farther away. And so we can build in the picture of the entire plume, the acceleration over the full length, by allowing the orbit to precess and to bring us into different parts.
In a way, it's kind of like tomographic. You start
Yeah.
getting slices at different altitudes through that plume.
And all the while you're doing this, you have to follow, rotate things in MSE coordinates, because you just can't. So you have to keep track of what you're doing and putting them in the right coordinate system as you do it. But yeah, that's right. I mean, it takes time for the orbit to precess all the way through the system to the point where we can map out in 3 dimensions what's going on. And then as a function of drivers, as a function of the variation of the drivers.
And I think I asked this question before. Will you eventually be able to characterize where the greatest loss is coming from, either through the polar plumes or through the down the magnetotail?
I think in combination of the models and the measurements that put constraints on the models. I think the model that I showed you from Shannon Curry actually uses static measurements as a baseline for what the ion density is, and then it has a certain number of test particles that it flies through, and each one is weighted by the density of the source region. And so you can actually design. You have to understand. You have to go from in situ measurements at a specific time and place and set of conditions to a global statement. And so one approach is to take Dave Brain's approach and make a shell around the planet, and then over time you map out exactly what escapes and what comes back as a function of all the conditions that go into that. And for a thing like this, mapping out and trying to map out the plume, you have to, and which loss channels are more important, you have to map it out as a function of the input parameters and as a function of distance along the plume, and map out the physics of what's going on, and then use the model to take those in situ measurements from a variety of different conditions and extrapolate what happens on a global sense. So you can use both models, the models anchored to the data to make that extrapolation, or you can take shells around the planet and make a similar kind of extrapolation. So we're using both techniques within the team. Okay.
I'm sorry, I just was trying to be courteous, but I've got one more. So are you seeing a distinction in terms of atomic mass of the ions escaping in the poles versus downstream? It seems to me like wholesale stripping of the higher mass ions would be more inclined to be down the magnetotail.
I don't have the answer to that one yet. Don't think we're at the point where we can answer that yet. But yes, there could very well be a mass distinction between whether the plume is more important or whether the tail outflow is more important. Right now, we've only done it for O+. The model has only done it for O+, but we can do that for other species as well. It just hasn't been done yet.
Question for you. So I know you worked a lot on the Mars reconnaissance orbiter, losing electrons.
You mean global surveyor?
I mean Mars global surveyor. What are you excited about MAVEN in terms of the data compared to the data you had before? So you now have access to this really rich data. How is it different?
Different in several very important ways. One is for Mars global surveyor, we had an electron instrument and a magnetometer. With MAVEN, we have a whole suite of measurements over a much wider energy range, all the way from below the escape velocity to far above the escape velocity. Both ions and electrons and magnetic field, all at a much higher cadence, much larger field of view. And the other thing about MAVEN is that its orbit is very different. Remember, the Mars orbit was designed primarily as an imaging mission, where it would take photographs of the surface and also laser altimetry of the surface spectroscopy. And so it was locked in a 400-kilometer altitude orbit, 2 a.m., 2 p.m. for most of the mission. And so what MAVEN does, instead of being locked in a single local time, it's able to sample many different altitudes and the orbit processes around the planet. And so we get to see not just the magnetic fields at 2 a.m., which is what that image was. This is magnetic fields at 2 a.m. We get to see them as Dave Brain's movie showed, as they rotate around and they're compressed on the day side by the solar wind pressure, and then as they rotate out into the dawn and dusk, they begin to open out and extend to higher altitudes, and then on the night side they extend all the way, to very large altitudes out the tail. And so just to see the dynamics of the magnetic fields as they're in different orientations is another really nice thing about MAVEN.
Are you already seeing? Were there times when you were just looking at the data from the? I cannot keep that name in my head. Mars
Global
Career, MGS. Were there times when you were looking at the data from MGS and you were thinking, oh, if only I could, be on the dawn and dusk side. If only I could see this, I would understand better, how the electrons or how the ions are moving out, or that you're already seeing. Like are you able to answer some of those questions?
For Mars Global Surveyor, back at that time, I came in, as I mentioned already, I came in after the mission was in the nose cone of the rocket. So, and we were much more conservative with MGS. And MGS went through an aerobraking phase, and it went down to altitudes, down to a little over 110 kilometers up to the lowest, 110, 120 kilometers, similar to MAVEN deep distance, and even a little bit deeper. But the Electron instrument was turned off because we were afraid of electrostatic discharges through the high voltage operation. And it turns out that we did a lot of work on MAVEN to prove to ourselves that we can actually operate just fine at those lower altitudes. The big difference with MAVEN is that we're keeping several instruments on. SWIA, SWIA, and static are all turned on and operating normally, even at the lowest altitudes, even deep dip altitudes. And that's a huge advantage to measure the plasma population along with the magnetic field down to those lowest altitudes. And so coverage of the plasma measurements as well, which is a big advantage for MAVEN. Did I answer your?
I get a sense that for what you're trying to do, are solar storms a complication? Is it better to have quiet solar wind conditions so you can establish a baseline and then map the solar storm aberrations on top of that? Or do you welcome having those solar storms because they
we welcome all the variability. You're right. We want to have context. So when you have a solar storm, you look back at the data. Okay, we need to have the baseline before the storm happened. We want to see what. You saw in the charts that the other two speakers have already presented. This is the before and this is the after. You always want to have the before and after, and so it's important to get the full range. So we'll take whatever comes.
Yeah. Is the relaxation during all of this solar storm days, weeks, hours?
Well, the solar storm itself can last many days.
Yeah, right.
But then after the storm is gone, I don't know, it's probably hours for the relaxation to take place. But yeah, we definitely welcome as much variability as the system will give. That's how we try to understand how it responds.